The first speaker is Professor Daniele Valtorta. He is from University Milano Bicocca, and he is the recipient of the Frontiers of Science Award this time. His talk is about the structure of singular sets of minimizing harmonic maps. Let's welcome.
Thank you very much, and thanks for the invitation to speak at this wonderful conference. Today I'm going to talk about the structure of the singular set of minimizing harmonic maps, even though some of the results that I'm going to mention are working also for stationary. This is a brief, no, the other way around. This is a brief outline of my talk. I'm going to introduce what are harmonic maps, and I'm giving you very basic examples of singularities for minimizing harmonic maps, and I'm going to state the main theorem. But most of the talk is going to focus on the proof and, most importantly, the ideas behind the proof of this result. I'm also going to mention some other applications, not of the result itself, but applications of the technique, which turns out to be quite flexible and can be adapted to different situations in geometric measure theory. In the proof in particular, I'm going to focus on two main aspects of the proof, which is, one is kind of a Reifenberg type theorem, and the second one is the L2 approximation theorems, but we will get into the details soon enough. So without further ado, let's get started. When you're talking about maps between Riemannian manifolds, you have a natural way of defining the Sobolev W12 space, and by this I mean you have a natural way of introducing what is the Dirichlet energy for such maps, and as good mathematicians, we like to consider critical points of this energy. For standard harmonic functions, so when the target is linear, when the target is Rn, R or Rn, you have the usual Laplace equation, Laplacian of u equal to 0. But in this case, the nonlinearity of the target introduces a nonlinearity in the Euler-Lagrange equation, and you immediately see that you have a Laplacian on one side, two gradients on the other side, and this is a recipe for disaster. In particular, elliptic regularity doesn't hold everywhere, and you may end up with singularities. The first and easiest, actually, and most important example of singular harmonic map, something which is not continuous, something for which elliptic regularity doesn't hold, is the usual projection from Rn into the sphere in the same ambience, so the sphere of one dimension less. Really just x over absolute value of x. We need to ask that the dimension of the domain is greater or equal than 3 for a stupid consideration. If you consider this map in R2, very simply, you can do a computation, and the energy of this map is infinity. So it doesn't make sense to talk about, it doesn't make sense to consider this an harmonic map. It has infinite energy, so it cannot be one of our examples. But from m, when m is equal to 3 or higher, each one of these projections is a minimizing harmonic map. So you see, even though we're talking about harmonic objects, these objects can develop singularities, and in particular they can develop discontinuities. You may wonder, okay, fine, this is, this fact makes these objects interesting because they are not as trivial as harmonic functions, but maybe you may wonder, okay, fine, you've given me an example of a discontinuity, but maybe there are more, other kind of singularities, kind of your function is continuous, but not Lipschitz or not C2 or something like that. This is not the case. As soon as you have continuity, elliptic regularity kicks in back again, and you have smoothness with all the estimates you want. So really, the enemy or the interesting thing about harmonic maps, depends on which way you look at it, are discontinuities, and I'm going to talk about those. Word of advice, especially for those of you who aren't familiar with harmonic maps, there are different kind of harmonic maps. When you're talking about harmonic functions, your Dirichlet energy is a convex functional, critical point and minimizer is the same. For harmonic maps, you have different notions because the nonlinearity of the target breaks the convexity of this function. In particular, you have weakly harmonic maps, which are critical points only with respect to target variations. They satisfy the Euler-Lagrange equation in the weak sense, but nothing more. Stationary harmonic maps are also critical points with respect to domain variations. And minimizing harmonic maps, as the word, it's pretty self-explanatory. Those are local minimizers. For the sake of convenience, and in order to try to avoid many technical aspects of this talk, I'm going to focus on minimizing harmonic maps and on the results on minimizing harmonic maps. All of the techniques that I'm going to talk about today do not apply to weakly harmonic maps, and as you heard in previous talks, there are examples of really wild behavior of weakly harmonic maps. But some of the results that I'm going to talk about apply also to stationary maps, and I will point out the difference when we arrive at that point. Okay, the main theorem that was proved in the paper with Cheeger and Naber is the following. Giving a minimizing harmonic map, you may have singularities, but the singular set is m-3 rectifiable. M is the dimension of the domain. M-3 rectifiable, and with these uniform volume estimates. Let me just spend 1 minute on a description of these results. What am I saying here? I'm saying that I consider my singular set, which is the set of discontinuities. I'm considering, in a finite, in a confined ball, I'm considering the tubular neighborhood of radius R around this set, which means I'm taking my singular set and I'm effectively fattening it uniformly by radius R, and I'm telling you that the volume, the full dimensional volume of these objects, scales like R to the power 3, which is the hallmark of having codimension 3 in your domain. It's a one-liner to realize that this immediately implies m-3 Hausdorff estimates on the singular set itself, but this is a lot more powerful and a lot more uniform in some sense. There are the results on the stratification of the singular set, and those are valid also for stationary harmonic maps, but we are not going to focus on those today because I would like to try to focus on the main ideas and not on the technical details. Important thing, the same technique can be applied to a slew of other problems in geometric measure theory. The easiest one is definitely the critical set of classical harmonic functions, or the critical set of more general of solutions to more general PDEs, but also in the past, 5 or 6 years, we've seen the applications of this technique applied to the free boundary in thin obstacle problem, liquid crystals, Young-Mills connections, singularities of minimal surfaces, Q-valued harmonic maps, and also the singularities, bounds on the singularities of Ricci limits. So, the technique is quite flexible. If I have time, I will try to tell you what are basically the main differences between the application of the technique to harmonic maps and the application of this technique in these other cases. Because sometimes you're in luck and it's really basically copy and paste and everything works. Just cosmetic changes are okay. Sometimes the adaptation of the technique requires significant work. So, it's not that all of these results are just easy adaptations. Sometimes you really need a lot of work in order to make this thing work. Okay, fine, but without further ado, let's talk about the proof. And as it is often the case in geometric measure theory, we have a holy grail that helps us in the analysis of harmonic maps, which is a monotone quantity. And in this case, the monotone quantity is the renormalized scale invariant energy. What do I mean by scale invariant energy? You're considering the Dirichlet energy, integrating over a ball of radius r, and you're rescaling it with the right factor. You have a ball of radius r in Rm, so you rescale by r to the minus m. You have 2 gradients, and you rescale by r squared. This is the thing, this is the factor that makes this thing scale invariant. Now, I promised you that I wouldn't dwell too much on technical details, but let me spend 1 minute to talk about a non-significant technical detail, but which saves you a lot of trouble. And basically, this is the monotone quantity, the usual monotone quantity, just an integral over the ball of radius r rescaled. You can consider, instead of the standard one, kind of a mollified one, which looks uglier in some sense, but it's a lot more convenient to use. The difference between these and these is just, the presence of a mollifying function. Instead of a cutoff function on a ball of radius r, you have something which is mollified. The ideas are the same. Philosophically, it's really the same thing. These two objects are really capturing the same property. But, and trust me on this, it's a lot more convenient to use this quantity when you're doing estimates. Even though you have estimates that are a little bit longer and look a little bit uglier, it's a lot more convenient to do that, and I wish we had realized it before writing the article, because the original article is written with these guys, but this one is a lot more convenient. So, I'm just telling you, if you come across monotone quantities, it might be a good idea to change the perspective a little bit and mollify it. And let me just give you a stupid example, which is, again, it's not a breakthrough, it's not a significant idea, it's just a technical detail. Let me just give you a stupid example of why this works. If you consider the derivative with respect to r of this guy, it turns out that it is this quantity, greater or equal than 0. But you immediately realize that I'm kind of cheating a little bit here, meaning that this integral over the boundary of a ball, is defined almost everywhere, so you have to be a little bit careful and blah, blah, blah. It works in the end. I mean, this quantity is monotone. But if you take the derivative of this guy, it looks uglier, but it's defined out of the bat everywhere. And you can take even derivative, gradients with respect to x, Laplacian with respect to x, you can do whatever you want. It's basically a mollified version, so you can, play around it with as many derivatives as you like. Maybe you will not find significant estimates for, the third order derivative, but still the fact that you can do it makes your life a lot easier. And that's it. For the rest of the talk, I'm going to focus on this quantity here, but if it bothers you, you can consider this quantity and this quantity replaceable from the point of view of interchangeable, I would say, from the point of view of philosophy, from the point of view of ideas.
Does that allow you to do epsilon regularity less regularity assumptions?
No, it's not that. It's really just technicality, meaning that when you're doing covering argument or estimates, here you have to scratch your head a little bit more, and you have estimates on annuli instead of balls, so you gotta be a little bit more careful. But from the point of view of ideas, you don't gain anything from in the results. It's just that the proofs are a lot easier. Just that, unfortunately. Or maybe you can find better things, better applications for this idea. Okay, fine. Monotonicity of our normalized energy immediately tells us something very, very nice, which is the fact that if you're considering your function defined on the ball of radius 1, for simplicity, at every point, you're going to have tangent maps, plural tangent maps. What do I mean by that? This is a standard trick. If you consider balls of radius r around this point, and if you blow them up to balls of radius 1, so you simply magnify your function around points, all these magnifications have uniform bounds on the energy, which means that they are pre-compact in the W12 sense. So you can take weak limits in W12, and at every point, you're going to find a tangent map, a limit of these guys. The limit might depend on the sequence you choose, on the sequence of radii that converge to 0. So, there exist tangent, again, maps, plural. It's not said that the tangent map is unique. I'm not claiming that. But at least, at every point, you have at least one tangent map, maybe more. Fine, and on top of that, every tangent map is going to be zero homogeneous, so it's going to have a very nice structure. By zero homogeneous, I mean that a tangent map, when you go to the limit, is going to be invariant, precisely invariant on the lines emanating from the origin or from the point you are considering. Why this is the case? Again, it's an easy consequence of monotonicity. When you look at the monotonicity formula, zero derivative for the monotone quantity means that you have zero gradient in the radial directions. And when you're considering, it's automatic from monotonicity that when you're considering a tangent map, the monotone quantity is constant for the tangent map itself, if you're centering it at the origin. Good, and now very, very stupid argument, easy, an easy drawing in Rn is going to tell you this. And it's going to tell you something which in general, it takes the name of cone splitting principle. The idea is the following. If you have an object with symmetry, like zero homogeneity in the case of tangent maps, symmetries at different points interact with each other to create higher order symmetry, which is a fancy way of saying the following. Suppose that you have a tangent map, homogeneous with respect to the origin. And suppose that by some chance, this map is also homogeneous with respect to another point, zero homogeneous with respect to another point. Homogeneous with respect to the origin means that the derivative in the blue direction is 0. Homogeneous with respect to here means that the green derivative in the green direction is 0. You sum them up, derivative in the red direction is 0. And the right direction is always this difference. It doesn't depend on the point you're considering, which means that your function is going to be absolutely, or your map is going to be completely invariant with respect to the line joining these 2 points. And you can see it also from the, from the equations. If you have, this is supposed to be green, but kind of. If you have the first line and the second line, by summing them up, you obtain that your gradient is going to be 0 in the direction joining these 2 points. And you can play this game with as many points as you want. If you have 3 points of homogeneity that span a plane, then your map is going to be invariant with respect to the plane spanned by these points. This is a very general principle that occurs very often in geometric measure theory, and sometimes it's called cone splitting principle. You're going to see it's a crucial principle in these kind of techniques, and it is, I don't know, embarrassingly easy, I would say, because it's really a drawing in a red, nothing more, at least in the case of harmonic maps. In other cases, it's a lot more complicated. Okay, one more technical ingredient before we move on. This is the only difference between the stationary and the minimizing case. I'm not going to give you a proof of the following lemma, but it's kind of believable that if you're considering a sequence of minimizing harmonic maps, and if you're considering a weakly convergent subsequence, W12, weak convergence is automatically upgraded to strong convergence, and the limit inherits the minimizing property. This is not trivial, not immediately trivial to prove, but kind of expectable in some sense. And this is, again, the only difference between, the only important difference from the point of view of our techniques between stationary and minimizing case. Come again?
Do you do some convexity of the energy to show the strong convergence?
No. The local minimizing property is enough. And it's encoded in what's called Luckau's lemma. I mean, it's a consequence of Luckau's lemma, which, if you ask me, is kind of a theorem more than a lemma, because it's not trivial. It's absolutely not trivial, but at least kind of believable. Let me put it this way. Ah, you think that's the... Luckau's theorem doesn't rhyme as well. Okay. But in any case, it's a deep result. Okay, now I've been blabbing about symmetries, homogeneity, and so on and so forth, but I promised you a talk about singularities. The next line, which is going to be, again, super easy, is the only link we need between symmetries and singularities. And it's the only part, it's the only link we need between these two concepts. The next lemma tells you that if you are considering a tangent map, which is n-2 symmetric, what do I mean by that? Tangent map means something that is zero homogeneous. Plus, we also add, let's see if I can use this, n-2 directions with respect to which your function is invariant. Then such a map is automatically going to be constant. And the reason is trivial. n-2 invariance means that basically your map is just defined on a slice, on a two-dimensional slice. And if you have a zero homogeneous map defined on a two-dimensional slice, either it's constant or it has infinite energy. And so it cannot be a tangent map arising from a weakly convergent sequence of maps with uniformly bounded energy. Okay, that's the only link we need. And remember that, tangent maps are going to be blow-ups of the original map at infinitesimal scale. If the blow-up has zero energy, so if in the limit you have zero energy, there's an epsilon regularity theorem that tells you, even before the limit, you're going to have, at a certain, maybe super small scale, you're going to have very, very small energy, and having very, very small energy means having no singularities at all. So this statement is, in some sense, rigid. Even before the limit, if your limit is n-2 symmetric, you're not going to have singularities on a very, very, very tiny ball around the point you're considering. But this, again, it's the only link we need between homogeneity and symmetry. Using these ingredients, and in particular using Federer's dimension reduction argument, Schöne-Uhlenbeck in the 80s proved that the dimension, the Hausdorff dimension of the singular set of a minimizing harmonic map is at most n-3, so it's at least codimension 3. I'm not going to give you, this talk doesn't want to be, a complete overview of all the results in history. Unfortunately, for time limits, I'm going to focus on the main ones, not on the main ones, but on the ones that are, closer to the techniques that I'm going to talk about. And in some sense, this is the first easy application of these ideas that are going to play an important role for us. So using just these ideas, Schöne-Uhlenbeck proved that you have Hausdorff codimension 3 for your singular set. Unfortunately, this argument doesn't give you rectifiability, just Hausdorff dimension bounds and no effective bounds. Okay, let me backtrack a little bit and take this statement. A tangent map which is n-2 symmetric is constant, so it doesn't have singularity. And let me rephrase it in a different way, which sounds a little bit more complicated, but it's exactly the same way. We have a dichotomy, in some sense. Either the points of zero homogeneity of T span a subspace which is at most three-dimensional. So either the points with respect to which your map is zero homogeneous span something which is at most n-3 dimensional. Wow. Or, it's going to come back, I hope. Or, stupidly, the point spans something which is at least n-2 dimensional. But we've seen that at least n-2 dimensional means no singularities at all. So the second, we can, on the second line, we can say that T has no singularities. And using a simple, very simple compactness argument, you can upgrade this statement to a rigid statement. So you can put an almost around and it still works. Basically, you can consider a map and you can consider on this ball the points with respect to which your map is not exactly homogeneous, but maybe close to being homogeneous. So here you have something which is not exactly zero homogeneous, but close to being zero homogeneous. And these points they're either, well, not exactly on a n-2 dimensional subspace, but contained in a very, very tiny strip around an n-3 dimensional subspace, so maybe something like this. Either you have these, or you have no singularity. And this is, again, the rigid version of the statement I made before.
In this picture, what we should interpret before you ask all the information.
Exactly. You don't need to go to the limit. You don't need a tangent map. You don't need exact zero homogeneity, but you can stop before. This statement holds also at finite scales. I'm being very sketchy in some sense, in the sense that, I didn't give you a full definition of almost zero homogeneity, but you can imagine that the definition is on this blue ball, you have a perfectly zero homogeneous map, which is close to your map in the L2 sense, W12 sense, something like that, in any reasonable norm for minimizing harmonic maps. And so you don't need exact homogeneity, you can stop a little bit before, and so you can stop also at finite scales. And this is very important. Again, this statement is, how to say, an easy consequence of a very easy compactness argument, and it is the key for the following result by Cheeger and Naber of around 2010. I don't remember exactly when. I'm not claiming that you have this result and then you have this theorem immediately. It requires a lot of work, but the statement I made before is the key to proving this result. And this result, you can immediately realize it's basically what I wanted to tell you, basically the content of this talk, up to the following epsilon. So it's really almost what we want. In some sense, the object of this talk is to get rid of the epsilon in this part. And it's absolutely non-trivial because as soon as you have an epsilon, you're not ruling out any fractal behavior of your set. I mean, the estimate with an epsilon doesn't rule out fractal behavior of your set. It doesn't prove rectifiability. You cannot have rectifiability from a statement which is even an epsilon distance, even at an epsilon distance from your power, from the right power. Okay, so historically, this is, and this argument is based on, it builds on the quantitative stratification, which was kind of introduced in Almgren's big regularity paper, even though it wasn't called this way back then. Okay, so the objective of my talk now is to get rid of this epsilon in the estimate. And how do we do that? I've given you this statement. Using a simple compactness argument, we have the statement I drew over there. So either the points of almost zero homogeneity are close to a subset of dimension n-3, or you have no singularities, which is the key for Cheeger and Naber argument. And in order to improve it, what I need to do is to quantify in a very, very sharp and precise and controllable way what I mean by almost zero homogeneous. So not hand-waving, but really quantify it in a very precise way. And the same thing I need to do for what I mean by close to a n-3 dimensional subspace. So these are the two key statements that I need to make more precise in some sense. So we start from the notion of closeness to an n-3 dimensional subspace. And I don't need to restrict myself to n-3 dimensions. I can give you a statement. I can give you an idea of what it is for a general k-dimensional thing. Those of you who attended Professor Tolsa's talk are already familiar with this guy. The right notion that we need to improve our estimates is called John's beta numbers. And it has this definition. Let me explain it to you very briefly. Consider, for the sake of simplicity, a set in Rn, and put the k-dimensional house of measure on it. You can do better. You can put any measure on it, but just for the sake of simplicity, let's put the k-dimensional house of measure on it, and we can consider the integral of the distance squared between this set and any k-dimensional linear affine actually subspace, and take the infimum over all possible k-dimensional subspaces. You immediately realize that these kind of arguments work very well with scale invariance. So I have a k-dimensional house of measure here. I should divide by r to the k. I have a distance squared. I should divide by r squared. So the r factors are just to make everything a little bit more scale invariant. It's evident that I made a bad choice here. I could have minimized. I could have reduced my beta number by considering a plane which is a little bit more, a little bit closer. But regardless, this is the definition, and this gives you a very quantitative and sharp way to quantify how close or how not close, how far away is your set at a given scale on a given ball from being exactly k-dimensional. Fine, and let me just mention, I cannot go through the proof of this result, but let me just mention briefly that this is important because there's a lot of literature with these, regarding these Jones beta numbers, and in particular, you can prove that if your set satisfies the following estimate, which is kind of ugly, so let's just say if your set satisfies the blue inequality, just to make it a little bit more simple, if the sum, the integral over all scales of your beta numbers is small at every point in your set, then your set is rectifiable and you have estimates. So you can play around with examples and you realize that if you have a smooth manifold, this is always the case. But actually, the work by Tolstoy and Zam also proved that in some sense, not in this precise, not in exactly in this sense that we need, but in some sense, this beta number really capture the rectifiability of your set with a necessary and sufficient condition. So it really looks like a sharp characterization of rectifiability. We don't just need rectifiability, however, we also need uniform bounds. And so this is why the statement is a little bit more complicated in some sense. But again, there's a lot of there's a rich literature on this subject. Fine. And as for the notion of closeness to something which is zero homogeneous, the monotone quantity will play the key role to make these quantitative statements. So the other thing that I needed to quantify in my statement was the notion of almost zero homogeneous. And it turns out that the right notion, the right quantity is the derivative of the monotone quantity, or, if you want, this should be a 1, sorry. This radius and this radius should be the same, so 1 and 1, R and R, or 1 and 1, it's a typo. But the derivative of the monotone quantity, or if you prefer something a little bit more fine in scales, the pinching between R over 2 and R over 4 of your monotone quantity is what actually controls very well the notion of closeness to something zero homogeneous. If the derivative of the monotone quantity is 0, you have something which is exactly zero homogeneous. Otherwise, what you obtain is that if this is small, using a simple compactness argument, if this is small, you obtain smallness on this side. And the right notion, the right link between how close you are to being zero homogeneous and how close your singular set is to being in a plane is given by the following lemma, which is the thing I'm going to focus on for the rest of the talk. And so let me discuss it a little bit. Here I'm saying that how close your singular set is to being contained in a plane is controlled by some weird and ugly looking integral involving your pinching, your monotone quantity. Okay, I want to do two things with this lemma. First of all, I want to convince you that it's the right lemma. Once we have this result, we can prove what I wanted to prove. And the second thing I want to do is to not give you a proof, because it's kind of involved, but give you a hint of why this actually works. No, it's actually important that this quantity here, this inequality here, works with respect to any measure on the singular set. I've been a little bit cheeky here. This quantity, you should define this quantity with respect to this measure, not with respect to the singular set. So yeah, you're right, I swiped this detail under the rug. This is not, yeah, if you want, you should take this beta number with respect to the support of your measure, something like that. Okay, so first of all, why is this true? What I'm about to say is wrong, but let's forget for a second about the black parts. Without the black parts, this estimate is wrong. Let's make believe that only the blue estimate is true. So the beta number is controlled by the pinching. Then, the Reifenberg theorem was asking us, we want to sum this thing over scales and get something which is controlled. That's how we wanted to apply the the Reifenberg theorem. But if the beta number is controlled by this guy, you're basically integrating a derivative, and this is how you get your bound. This is how you get your control. I'm cheating a lot, and actually the black part is essential. You cannot, take it away. And it requires a lot of covering arguments, a lot of technical details, and a lot of ideas also to be handled. But roughly speaking, this is the core of the argument. So I hope I convinced you, maybe not, but given you a hint of why this estimate is useful. Now let me try to convince you that this estimate is true, if I have enough time. Yeah, 10 minutes should be okay. And let me try to convince you that this estimate is true by proving it in a very, very, very simplified scenario. So let's consider a very stupid scenario where we have a singular set, an harmonic map with a singular set made by, in R3, made by 2 points, which with unparalleled fantasy, we're going to call x and y. So we have 2 points, x and y, the only 2 points, the only 2 singular points of our harmonic map for the sake of argument. And let me try to show you that this lemma is true. So first of all, let's make a few simplifications. The beta number I have on the left was squared was what? It was the infimum over all n minus 3-dimensional planes, which in this case means the infimum over all points of the sum of the distance squared between these 2 points, which is the point which realizes the infimum. It's the center of mass. And up to a constant, the beta number is really, in this case, is really just up to a constant. It's the distance between x and y, nothing more. So in this easy scenario, we know, this is really, really something easy. And on the other side, the integral over this pinching at scale 1 is just the integral with respect to, direct delta at x, direct delta at y. It's a sum. It's a sum of the 2 pinching. So this is what, distance between x and y squared bounded by a constant time times the sum of the 2 pinchings is what I have to prove in this case. And the proof is, the proof of this simplified case is, again, embarrassingly easy, meaning that on the one hand, we know that our harmonic map, if it has singularities, it must have some energy. It cannot, if it has singularities, it cannot be close to something which is n minus 2 symmetric, which means 1 symmetric in this case. It cannot be close to something which is 1 symmetric. It cannot be close to something which is invariant with respect to any line. And in particular, it cannot be close to something which is invariant with respect to this line, for example. An effective way of saying it is that the energy along any n minus 2-dimensional subspace, in particular the energy along this line, has to be at least something. It needs to have at least some lower bound. So you have a constant independent of everything, and the energy of your harmonic map along any line has to be at least this much. Otherwise, you would have something which effectively is almost n minus 2 symmetric, which means it cannot have singularities. In order to close this argument completely, you just need a compactness argument, super easy compactness argument. Okay, we'll use this estimate in the next slide, basically. And how does the pinching of our monotone quantity play a role? Well, recall that we have this estimate, which up to a lot of frills, if we take r equal to 1, just to make everything a little bit more simplified, and let's forget about this for a second. This estimate gives you bounds. The pinching gives you bounds on the energy of u in the direction z minus x, where z is the point you're integrating, and x is this point here. So z is a point here, and x is your singular point. You have these for x, you have the same thing for y. And now consider the following. Again, stupid, simple drawing in R2. Y minus x can be written in terms of z minus x and z minus y for every z. I'm saying something trivial, absolutely trivial. And you can use the principle, you can use this drawing to estimate this quantity. The gradient of u integrated in z with respect to the direction, scalar product with the direction y minus x. And now, y minus x can be bounded by z minus x plus z minus y, and so up to a constant, you see that the energy in this direction can be bounded by the sum of the two pinchings at x and at y. But on the other hand, so on the one hand, I've just shown you, or just kind of hand-waved my way through proving this estimate here. But on the other hand, if you look at it, this guy here is the energy along a unit direction times x minus y squared, the distance between x and y squared. The energy in any direction we've seen that is bounded from below by a constant. And so putting everything together, you have the distance between these two critical points, singular points, is bounded by the sum of the pinching at x and y. Now, in order to prove the general statement, the general lemma with a generic measure, and so on and so forth, what you need is this idea plus a lot of, not even that much, plus some linear algebra. You need to define a few quadratic forms, and so on and so forth, but it's really not very deep as a result. It's really, really super easy. And this is the last step that I wanted to show you, meaning that this is the last key ingredient in the proof that is needed to prove the main result that I stated at the beginning. Needless to say, I swiped a lot of details under the rug, really a lot of details. Just to name a few, everything needs to go through. In order to make all the argument work, you need to come up with clever covering arguments. You need to cover your singular set and to split it up into a lot of pieces. You need to have a double induction in order to make all the estimates work. One induction upwards in the scales, one induction downwards in the scales. And I've also haven't talked about the fact that our results not only work for the singular set, but they also work for the quantitative strata of the singular set. I haven't even told you what the quantitative strata is, actually. But basically, bottom line is, you can take these results and make them even more quantitative in some sense. Just to give you a hint, with these results, you can even prove better integrability for the gradient of u in the minimizing case. So you can show that the gradient of u is not exactly in L3. That's not possible. You have counterexamples to that. But it's all the way to weak L3. So the gradient of u a priori is just L2, has L2 integrability. If you have a minimizing harmonic map, you can show weak L3 integrability. And there are a lot of other details that I haven't talked about. There's a lot of other things that are important in the construction. But that's basically the gist of it. I hope with this talk that, for sure I haven't been able to explain to you all the details and all the important parts of the ideas, but maybe I was able to convey, to paint a general picture of what's going on. And again, since this technique can be applied and has been applied in various different scenarios, maybe once you have the ideas in your head, you will be able to apply to other situations, or you will be able to improve it, streamline it, whatever. That was kind of what I wanted to do with this talk, and I thank you very much for your attention.
Thank you. Any questions?
Yeah. Can you get some quantitative estimates, such as something close to uniform rectifiability, or maybe, yeah, possibly you don't get lower irregularity, I'm not sure, but maybe you could get that the set is contained in a set that is like irregular, something like that, and then obtain some good estimates about related to uniform rectifiability.
Okay, so the point, I mean, the real issue there is that, sorry, I forgot my chalk. The issue there, as you said, is that I don't get lower bounds. So in some sense, the singular set, you know, if I know a priori that the singular set is lower half-force regular, then automatically you get uniform rectifiability out of it. But unfortunately, it might very well be, and it is an important feature of the technique, you may have a lot of holes in your singular set, and you may have so many that actually your singular set doesn't have any uniform rectifiability. Actually, I think that Leon Simon's talk on the structure of the singular set for minimal surfaces, if it can be applied in this scenario, it will destroy any hope of uniform rectifiability here.
Yeah, maybe a remark, but having estimates on the Minkowski content that you have, maybe with that you get that this set could be contained in a set that is uniformly rectifiable, something like that, maybe.
Contained in a set that is uniformly rectifiable, maybe one has to be careful because, I mean, I would need to think about it more, but one has to be careful because, for example, I mean, basically what we do is, as long as your set looks quantitatively lower half-force regular, then you can build a set that contains it in a quantitative way, but when you stop and you create holes, you destroy the structure. Yeah. There is the example, I mean, it's not really related to harmonic maps, but there is the example by David and Toro about, you know, the small Möbius strip that cannot be covered by a single map. I think that would give you some problems here. But with some work, I don't know, I'm 50-50. Maybe yes, maybe not. I haven't actually thought about it.
All right. May I have another question? So,
sure.
Do you think that your techniques could help to study the uniqueness of the blow-ups in these problems, for example?
The answer is absolutely not, and it's
that you don't know, or that does not help. Sorry.
It doesn't help. It doesn't help at all, and it's important that it doesn't help because we don't want. I mean, in some sense, you know, this is the key. -3. We just know that this quantity is barely summable. If you were able to say if you're able to have some decay, then fine. But getting a decay is super hard. We wanted to sidestep the whole process of decay, and so this technique cannot help you in improving uniqueness of tangent maps. But you do get something, not exactly not the uniqueness of tangent maps, but you do get that at n-3 almost every point, not the tangent map is unique, but the invariant direction of your tangent map is unique. So a little bit less that you can get, but the uniqueness of the, I mean, around the invariant direction, you can have as much, you know, shenanigans as you may want.
Okay, thanks.
More questions? Okay, if no more, let's thank speaker again.
Thank you very much.